Here's the notes for functions and their properties day 1. You can read the learning targets. Basically, we're going back over a bunch of vocabulary and maybe some new vocabulary when it comes to functions and their properties. It's going to take us 2 days to go over all of this content, so today is day 1. We start off by remembering that the domain is the input of a function and the range is the output of a function. Okay, so the domains go to the range because inputs go to the outputs. Okay, we also say that a function is from a set of a domain to a set range. That is a rule that assigns a unique element in the range to each element in the domain, which is a really, really fancy way of saying no repeating domains, or the x's cannot repeat. Okay, if the x's in the function are not repeating, that's considered a function. If it is repeating, it is not a function, it is just a regular relation. You can look at the x values if they're listed. Otherwise, you will perform the vertical line test to be able to determine if that relation is a function. So if any vertical line touches the graph more than once, that graph is not a function. So we have 4 examples here. We're going to state the domain and range of each and then tell if the relation is a function. Examples A and B are pretty simple because they're just coordinates. This is a discrete relationship since it's just coordinates and it's not continuous or connected. So we talk about the domain and range in a discrete way. The domain is the list of values of the x's, so -3, 4, and 2. The domain is the list of the y values, so -6, 0, and 2. I put these in number order because I'm a little extra, but you can just list them in any order. So you could have said 0, 2, and -6. I'm just annoying enough to put them in number order. And then this one is a function, example A, because none of the x values repeat. Each x value is unique, -3, 4, and 2. But on question B, the domain here has 4s, 9, and -9. You don't have to put the 4s in there twice since they repeat. You just have a domain of, again, I put it in number order, -9, 4, and 9. But you can put them in the order that they appear. This could have been 4, 9, and -9. And again, with the range, you just list out the numbers. They don't have to repeat, or they should not repeat, so you don't have to put -3 in here twice. And they don't have to be in number order. I'm just extra enough to do that. But since those 4s in the domain repeat, that's like the vertical line test failing. This is just considered a relation, which is saying not a function, because the x value of 4 repeats. Now the next 2 are graphs. We have a graph of a circle here, and we can still tell the domain and range, but it's helpful to think about the domain and range, potentially throw this back to Algebra 1, if you remember, Dolor the robot. Dolor the robot helps me remember that domain is describing the graph from the left to the right, and range is describing the graph from the bottom to the top. That's what we're doing. We're describing the intervals in which the graph exists on the left to the right, or the x-axis, the domain, and then the bottom to the top, which is the y-axis, or range. So if you look at this circle, on the left to the right, on my x-axis, it goes from -4 to 4. So my domain is saying from -4 to 4 inclusive, including the numbers -4 and 4, which is why we use the brackets. And my range, on the other hand, goes from -4 to 4 on the y-axis. That's the interval in which the graph exists on the y-axis. Now this is a relation because if we were to do the vertical line test, bloop, that vertical line crosses the circle twice. For every one vertical line, it crosses it twice. So this is just a relation, not a function. It fails the vertical line test. So next one is very interesting. So if you look at this function, this polynomial function here, bloop, 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 we're still going to do the domain and range. Domain is left to right, and range is bottom to top. If I follow this graph out to the left, we're going to get as far left as we can go. This graph never stops going out to the left, which means it's headed towards -infinity. And then if we look at the right of the graph, as it's going further and further this way, it never stops. Like there's no end point. So this graph in Algebra 1, you would have said all real numbers, but in interval notation, you say -infinity to infinity. Since you can't actually ever reach infinity, you're going to use the parentheses instead of the brackets. And for the range, again, since the graph goes on and on in the bottom, there's no bottom number. It's going towards negative infinity. But the top has an endpoint. It doesn't go any higher than 4. So 4 is my endpoint on the top. My range is simply from negative infinity all the way up to 4 inclusive bracket, since it exists at 4. And this one is a function because if I drew any vertical line on here, it would not cross that graph more than once. It passes the vertical line test. Cool. So on this page, we're talking about the domains of functions, and we're going to find these domains algebraically. Now, typically, for many functions, the domain is just all real numbers, right? That fun and funky R, or negative infinity to infinity. That's all real numbers. Normally, that's going to be your answer for any typical function, many of the functions. But there are 3 rules that keep us from doing that. If you have a square root function, the radicand inside that square root, the stuff inside the square root, cannot be negative. Okay, so we would have to put the radicand, whatever's inside that square root, as greater than or equal to 0, and then add those numbers to our number line. If we have a rational function, the denominator can't be 0. Does not matter what the numerator is, unless it's one of these functions. The denominator can't be 0. So one of the restrictions we will check on is taking that denominator and setting it not equal to 0. And then last but not least, the logarithmic function, the argument, which is the stuff inside the parentheses, cannot be 0 and cannot be negative. So what we'll do is we'll take that argument and we'll set it greater than or equal to 0, and then solve to see where the holes in the graph are, or where the graph actually appears on a number line on an x-axis. Okay, so typical functions, pretty much everything other than a square root, a rational, or a logarithmic function, you're going to be able to answer right away that the domain is all real numbers, like question A. That's a quadratic. It's a squared function. There is no restrictions on a quadratic, so the domain is all real numbers, or we say from negative infinity to infinity. However, if we look at B, B says h of x is equal to 1 over x plus 3. Well, that right there is a rational function. We have a denominator, and since we can't divide by a 0, that's not a thing, okay? We know that this denominator cannot be equal to 0. If we subtract 3 from both sides, we also know then that x can't be negative 3, because that's what would make it 0. So since we're writing this in interval notation, we need to figure out how to write that. And since I'm a visual learner, what happens best for me is if I draw a number line and add that hole or that certain point that's important on this number line. Does not have to be a fancy number line, just put the number on there. We are saying that for this function, everything's okay except for negative 3. So all the way from negative infinity, which is what's happening as this goes this way, all of that counts. But we have a little hole at negative 3, and then everything after that counts all the way to infinity. So the domain is negative infinity to 3 with a union at 3 to infinity. Negative infinity to negative 3. Those should be negatives. Bloop. Negative 3. All the way to infinity. Okay. I'm not going to talk through answer choice or problems C and D, because if you just follow through my work, you can kind of see. So pause the video right now and kind of look through the work. We've taken the logarithmic function, and we know the argument, stuff in between, can't be greater than 0, or must be greater than 0, sorry, must be greater than 0. And so x must be greater than 5. And so we have our domain. And for D, the square root function, the radicand, or the stuff underneath the square root, has to be greater than or equal to 0. So again, I can solve for x and then plot it on a number line and see where the domain exists. I do, however, want to talk about questions E and F because they're kind of fun. If you look at question E, we have f of x equal to x plus 2 all over x squared minus 6x plus 8. Well, we know that the only restriction on this kind of function, is that the denominator here cannot be equal to 0. Okay, so when we get more information about this, since it's a quadratic, we do need to factor it. So we would factor this with the guess and check method. Use the zero product property to know that since this can't be 0, then pretty obviously x minus 4 can't be 0 and x minus 2 can't be 0. So x can't be 4 and x can't be 2. So here's my number line. Okay, I have holes right here at 2 and 4. So there's a hole. It didn't really look like a hole a second ago, so I'm trying to make it look more like a hole. And then here's a hole at 4. Everything else on this number line works except for 2 and 4. So I have 3 little regions here. I have the region from negative infinity to 2. I have the region from 2 to 4. And I have the region from 4 to positive infinity. All of those intervals create my domain for this function because it works everywhere unless x is 2 and x is 4. Because then the denominator would be 0 and everything breaks. In answer choice F, I really like this example. It's kind of fun. So we have 2 problems with this one. First of all, the numerator has a square root, so we know that this radicand has to be greater than or equal to 0. And we have a denominator here. We know that the denominator can't be equal to 0. So we have 2 different restrictions here that are going to change my domain. We solve the inequality, x plus 7 greater than or equal to 0, which means x has to be greater than or equal to negative 7. And then we factor and solve this guy down to find out that the zeros that it cannot be are 4 and negative 3. So again, I think best when I'm on a number line. So here's my number line with negative 7, filled in circle, a hole at negative 3, and a hole at 4. I need to describe this interval. Well, this blue part right here says x has to be greater than or equal to negative 7. So I'm going to go greater than negative 7. And I'm filling in greater than negative 7, but when I arrive at negative 3, bloop, I have a hole. And then I keep going. And then bloop, I have another hole at 4. And then I keep going. Because it's all greater than negative 7, just not including negative 3 and 4. So my domain is from negative 7 inclusive to 3, and then pick back up at 3, go to 4, pick back up at 4, go all the way to infinity. And that's my domain. The rest of these notes basically goes over vocabulary. So super simple ideas with complicated vocabulary is what's happening here. We're going to talk about continuity. In non-technical terms, a function is continuous if you can draw the function without ever lifting up your pencil. And that's honestly a great definition for what's happening here. So in these examples, for these 4 things, we're going to decide if it's continuous or discontinuous, but then also label each type of discontinuity as removable, which means it can be plugged or filled in with a pencil, or non-removable, which means it cannot be filled in with a pencil at some sort of jump, vertical asymptote, or another super not dot type of discontinuity. Okay, so the first example here, we have 4 of them. If you notice, as you're drawing this graph, you're drawing and then all of a sudden, bloop, you have a hole in the graph. It's called a break or a hole. That makes it a discontinuous graph. And this break or this hole is a removable discontinuity because if I took my pencil, I could plug the hole essentially. That's a removable discontinuity. The top right one, if you notice, here's this function, and all of a sudden, bloop, we end up down here. Pretty obviously, I had to pick up my pencil for that, so it's discontinuous. And this is a non-removable discontinuity because I can't just plug it up with a pencil. In fact, this is called a vertical asymptote because it's a line that this graph is going to get closer and closer and closer and closer but never touch, and come from closer and closer and closer but have never touched it, a vertical asymptote. This last one is also discontinuous because, bloop, I had a jump. It's called a jump. Literally, it's called a jump in the y values. It's a non-removable discontinuity because I can't plug that with a pencil. And then last but not least, we have a nice pretty graph that is continuous because I could draw that whole thing without picking up my pencil. Now we have different intervals on the functions that we're also going to need to describe. These are the increasing and decreasing regions on a particular function. I cannot underestimate, or I cannot emphasize, that's the right word, how important it is to remember that you are just reading the graph from left to right. Do not follow the arrows because they're tricky. Read it like you read a book from left to right. Okay, the example down here kind of shows what decreasing, constant, and increasing looks like. It's pretty obvious. If the graph is going down as you read it from left to right, it's decreasing. If it's staying exactly the same, it is a constant function or constant part of this function. And then if it's going uphill, it's increasing. Okay, so you can talk about the different intervals in which that occurs. And we're going to do that on the back page here. Again, I cannot emphasize enough, read this from left to right. Do not let those arrows trick you. Okay, this graph is increasing on the interval from 2 to 3 and from 3 to 4. And so many students think that this is decreasing because the arrow is going down. We're not reading the graph this way. We read the graph from left to right. It's increasing as I go from left to right. That's a little tricky arrow. Don't fall for that. This graph is also decreasing on the interval from 0 inclusive to 1 exclusive, open hole, and is constant from 1 inclusive to 2 exclusive. It's pretty simple. Just don't let those arrows trick you when it comes to increasing and decreasing functions. Boundedness is a pretty simple concept as well. If a graph is considered to be bounded below, that means that there is a y value that is less than all others. So think about a quadratic. A positive quadratic has a minimum point. It has a bounded point because there's nothing that goes lower than this. There's a y value less than all others. Bounded above is the opposite. This is a negative polynomial because it's opening down. And it has a highest point. It's bounded above by something. There is a y value greater than all others. And then just regular bounded truly means that you're bounded above and below. So there's a highest and a lowest point, and it doesn't go higher or lower than that. So you can think of your constant functions or a sine curve. Your sine curve floats back and forth like that. I'm not a very good artist, so please don't judge my sine curve. But it has a bound on the top and a bound on the bottom. And then there are such things as unbounded graphs. So a typical like linear equation is unbounded, no largest or smallest y value. A cubic function is unbounded because there's no typical largest or smallest value. So some of your odd functions will be typically unbounded. And then the last piece of vocabulary we're going over today is about absolute and local extrema, which is the fancy way of talking about maximums and minimums. Now there's different types of maximum and minimums. They make up your extrema or extreme values. Okay, a local or relative extrema are the y values bigger or smaller than the other y values on the left-hand side and the right-hand side, which is essentially saying it can't like end at a local relative, what are the word? Extrema. Wow. But if it has an actual hill or valley happening, you can actually call that a local relative extrema. An absolute extrema are the biggest or the smallest of the local or relative extrema. So it's bigger or smaller than all other values. This one can be an endpoint because you know that it's the largest or the smallest of that function. So if we see here, please notice that these are out of order here, but I've color-coded them for you. Letter A, that's an absolute minimum because that's the lowest that it goes. Makes sense. B is neither because it's not the highest nor the lowest, and we can't call it a local extrema because we don't know if it just keeps going down or goes back up here. So it's neither. No right-hand side to compare it to because it could go like this or it could go like that. C is a local or relative maximum because it's not the highest point, but it is definitely higher than the stuff around it. It makes a hill. D makes a true valley here, so it is a local minimum. It's not the lowest, but it is a low point. And then E is your absolute maximum because it is the highest point that it gets to. It is a maximum, but it's the biggest maximum, so it's called the absolute maximum. And that is the end of our lesson for today. See you guys in class.